Alba Lia Masiello from Inda, and she will tell us something about a quantitative result for the k-Hessian equation.
Thank you, Matteo, and thanks to all the organizers for organizing these events. Today I will tell you something, a quantitative result for the k-Hessian equation, and our contribution to the topic is mainly contained in a joint work with Francesco Salerno from Naples. So the setting I'm starting with is something that Gloria already introduced on Monday. We start with n times n symmetric matrices, and this symmetric matrices has n eigenvalue. To this n eigenvalue, you can associate n numbers that are the k-symmetric elementary function of the eigenvalue. The first one, all of us know, is the sum of the all eigenvalues, so it's the trace of the matrices. The last one, when you choose k equal to n, you should know it, is the product of all the eigenvalues, so it's the determinant. And in between, you have other symmetric elementary functions. And what we want to do is to build a differential operator. So we will apply this symmetric elementary function on the matrix, on the Hessian matrix of a C2 function defined on a set omega in R to the n. And what we are interested in today is the k-Hessian energy. So we will consider throughout these 10 minutes a bounded convex subset of Rn and a C2 convex function defined on this set. We can define this k-Hessian energy, and if you think that when you choose k equal to 1, this operator is the trace, so when you choose k equal to 1, this differential, this k-Hessian energy is nothing more than the Dirichlet energy, as we are considering a function that vanishes on the boundary of the set omega. And this well-known Dirichlet energy is known to behave well under a symmetrization, a very famous symmetrization, that is the Schwarz symmetrization. As in this talk, I will think about a convex function that vanishes on the boundary of omega. My function will be negative, and so that's why I make this picture, which is not the one that you might be used to. And so what does this symmetrization? This is a symmetrization procedure that, starting from any measurable function defined on a set omega, gives you a function defined on a ball with the same measure, and that has the property to be radially symmetric and decreasing. And so with this function, of course, is linked to the first one, and in which way each sub-level set of the new function has the same measure of the sub-level set of your initial function. These properties allows you to preserve all the LP norm of the function, and also if you're considering a Sobolev function, so for which the Dirichlet energy is finite, you know that the Dirichlet energy decreases under this symmetrization. And these two properties well adapt for solving some spectral problem or some optimization problem in which the quantity that you want to optimize can be expressed as the minimum or the supremum of a Rayleigh quotient in terms of some LP norm of the function over some LP norm of the gradient of the function, such as the torsion problem that many of you introduced to us during this conference. And indeed, if you know that this problem admits a maximizer, and you know that this is the case because the solution to this PDE maximizes this Rayleigh quotient, and if you know that you can apply the symmetrization to this function, Schwarz symmetrization, you only need to have a measurable function, so in this case you can proceed in this way to, you can symmetrize the function and obtain something that is admissible on a ball and prove the Sum-Venant inequality. So the question that will interest us today is if there exists a symmetrization that suitably adapts to the k-Hessian energy in the same way that the Schwarz symmetrization adapts to the Dirichlet ones. And the answer is yes. And to tell you what this symmetrization does, I have to tell you what the Quermass integral of a convex set are. So you can think about these quantities as geometrical quantities that describes the shape over your set, and they appears in this formula, that is this Steiner formula for the volume of the Minkowski sum between a convex set omega and a ball of radius r. So this coefficient here that appears in front of the power of rho are the Quermass integral of the set omega. And some of these geometrical quantities, you already know them, because the first one, when you choose I equal to 0, is exactly the volume, while the second one, up to this factor n, is the perimeter. In between, we have other geometrical quantities, while at the end, you obtain just a number, which is the measure of the ball of radius 1 in R to the n. And so, what you can do, starting from a convex function defined on a convex set omega, you want a convex function in order to have a convex sublevel set of the function. So it's not really necessary to have a convex function, it's enough to have a quasi-convex function in order to define this symmetrization. So what is a quasi-convex function? It's a function whose level sets are convex. And what you do with Schwarz symmetrization, you used to preserve the measure, so the first Quermass integral, the one that you obtain when you choose k equals to 0 of the sublevel set, and build a radially symmetric and decreasing function. Now you want to preserve a Quermass integral. So given a convex function, you can define n symmetrization. And so when you obtain in this way a convex function defined on a ball, and it is radially symmetric and increasing. And if you remember, I told you that. Okay. So what is we have n symmetrization, which is the one that decreases the Hessian energy. Is if you start with the Hessian energy with k here, then you have to apply the k minus 1 symmetrization in order to have a polyazigo type inequality. Moreover, this inequality that was proved by Zhou in 1981 is also rigid in the sense that you can have equality here if and only if your set omega is a ball and your function is already radially symmetric and increasing along the radii. Some other properties of this symmetrization is that an isoperimetric property of this Quermass integral allows you, that is known as Alexander-Fencelli inequality, allows you to tell that all the LP norm increases under this symmetrization. So you have that the Hessian energy, so the analogous of the Dirichlet energy decreases, while the LP norm decreases. And where our contribution comes in this setting is improving a quantitative improvement of the polyazigo type inequality. So this first term here, greater or equal than 0, was the inequality proved by Zhou that tells you that the Hessian energy decreases under symmetrization when you fix the k minus 1 Quermass integral. And this inequality holds true with equality only if you start with a ball. And so what we do is bound from below the gap in the polyazigo inequality in terms of the distance. With this distance here is the Hausdorff distance of the set omega to a ball, which is suitably chosen. And the power here is far to be optimal. We don't know if this power here is optimal. And the constants that appear in front of the Hausdorff asymmetry depends only on the datum of the problem. So it depends on n, k, and it depends on the k-1 square mass integral of the set omega, which is the one that we are fixing. So I think that I can mostly stop here. This is the definition of the Hausdorff asymmetry. And just to conclude, I told you that the symmetrization procedure worked well on quasi-convex function, but I told you that the quantitative improvement holds true for convex functions. And we are able to generalize our results not to all quasi-convex functions, but to functions that enjoys this property to be p-convex for some p between 0 and 1. What does it mean? That when you take the function and you erase it to the power p, it becomes convex. Okay, and so for instance, this applies to the solution to this equation in R3. And so I think that I can stop here. Thank you for your attention.
Thank you very much. Questions for Alba Lia? Doesn't look like there are questions, so thank you very much once again for this.